Okay, welcome to day 6. We're going to do polynomial functions. These functions, you've done these before. We're going to graph and write equations of polynomial functions. So polynomial functions are graphs that are going to maybe look like this, or maybe something like this, or so on and so forth. Every term of a polynomial function has to be in the form of ax to the n. A is just some coefficient up front. It could be a positive, negative, decimal, fraction, doesn't matter. Raised to the x raised to the n, and n has to be that exponent. This exponent has to be a whole number. No negatives, no decimals, no fractions. So when we do standard form, and I write something in standard form like this, I do it from highest to lowest exponent, and that highest exponent is called the degree. And you can see I have all these terms here. So the leading term here, x to the n, has a coefficient a sub n, and so on and so forth. So we're going to look, what is the most important term? The most important term is this leading term up front. I'm going to get rid of the subscript n. So the leading term is the most important term, and that leading term is ax to the n. And we're going to break it up into pieces because each little part has to do something with what we're going to graph. The first part is what I call this leading coefficient, the number up front. And the leading coefficient a, so if a is equal to a positive number, that means the right side of the graph will go up to infinity. And if a is a negative number, that means the right side of the graph will go down to negative infinity. So that leading term has two parts to it. The first part is the leading coefficient, a. If a is positive, the right side goes up. If a is negative, the right side goes down. The other part that we have is this exponent, n. It is called the degree of the polynomial. The highest n is the degree of the polynomial. If it's a second degree, we call it a quadratic. If it's a third degree, we call it a cubic. And we have fourth degree, fifth degree, and so on and so forth. That will tell you a couple things. The degree will help you with the other side, the left side of the graph. So if n is an even number, square to the fourth, the left side will do the same as the right side. Okay, so if the right side is up, the left side will also be up. And if n is equal to an odd number, the left side will do opposite as the right side. So something that has an even degree, both sides either go up or both sides either go down. And something that has an odd degree, the two ends are opposite. If the right side goes up, the left side goes down, and if the right side goes down, the left side goes up for an odd degree. So that's my degree part, but it also does another thing with how many twists and turns a function can have. So I'll use pink. It would have, the n degree also says that it has at most n x-intercepts. We have seen this already with quadratics. An x squared function could have 2 x-intercepts. It also could have 1 or 0 x-intercepts, but it could not have 3. It would have at most n x-intercepts. And then finally, it would have at most n turns, or what you want to call bumps, what I call peaks and valleys. So if something is like a quadratic function, a parabola has one turn, one min and max. You want to call them mins and maxes, that's the same thing. An x to the fourth power could have up to 4 x-intercepts, up to 3 turns in the graph, or what I call 3 peaks and valleys. Now there's one other term in here that does matter. And the only other term that matters in standard form is this very last term here. This very last term, a sub 0, is called a constant term because there's no variable with it. And because it's constant, it will always be the y-intercept. Because when you plug in x equals 0, all those other terms will go away because they all have an x with it, but that last term is constant. There is no variable with it, so we get that final number. So let's try to sketch some graphs. These are not going to be accurate graphs. This is just what is the idea. So when I look at this problem here, I see my leading term is 8x cubed. Well, because it's a positive 8, the right side goes up to infinity. And because it is an odd degree, the left side does the opposite. It goes down to negative infinity. So I'm just going to draw little arrows here. Right side goes up, left side goes down. Because it's 3, it could have up to 3 x-intercepts. It could have 1 or 2, but it couldn't have 4. And the y-intercept is this last term here of 5. And I could just put 5 anywhere. I'll put it here. Now I don't have to be at those arrows, but I do want to go from the left arrow to the right arrow. I want to be down on the left, up on the right, and up to 3 x-intercepts. So here's a possibility that I could draw. Something like that. That's one possibility. I could also drawn something like this. You know, I need more details to see what's going on. So this leading term is really, what we're doing now is a big picture idea, a global view of what's going on, what the ends are doing, and maybe something else, and how many turns it has. Next example, I see my leading term is negative 3x to the fourth. And because of the negative 3, the right side goes down to negative infinity. And the left side, because it is a even exponent 4, the left side also goes down to negative infinity. So I'll put little arrows going down. X to the fourth means it's going to have up to 4 x-intercepts. And my y-intercept is negative 9. I could just put negative 9 here. So I could do something like this. 1, 2, y-intercept 3, 4 x-intercepts. And the left side and right side are both going down. That is a possibility. I also could have done this. Maybe something with no x-intercepts. Okay? It still meets our criteria. The left and right side are both going down. It goes through negative 9 as the y-intercept. And, you know, the next page we'll do more with what is actually going on. So when we have it in standard form, we get a global look on what's happening to the graph, the ends of the graph. Okay, in this page, we're going to look at better details. I really want to know exactly what's going on with this graph, so we're going to do more of a local view of the graph where we're going to see x-intercepts. So we're going to do the factored form. We did a factored form of a quadratic parabolas, and we had 2 sets of parentheses. Well, a quadratic technically is a polynomial. A polynomial, though, could have many x-intercepts. Could have more than 2, and that's what we're going to do today. So all these parentheses with the x's, those r's are all the roots or the x-intercepts, and we're going to take those factors, those things in parentheses called factors, and we're going to make them into x-intercepts, and we're going to graph things. We're going to look at leading terms, and so on and so forth. So when I look at this, the x-intercepts, I see 3 x-intercepts here. Negative 5 is the first, negative 1 is the second, and you got to be careful here. It's backwards, but this x-intercept is 2. When I want to do the leading term, I'm going to multiply this out, And when I see this, I see a 3 up front. I see in the first parentheses an x. I see another x. I see then a negative x. I'm going to write that a little bit better. I see a 3. I see an x. I see an x. And then finally I see a negative x. And I multiply that out. I get negative 3x to the third. And what does that mean? That means my right side is going to go down to negative infinity because of the negative 3, and my left side is going to go up because of the exponent being an odd number. So I'm going to put little arrows, right side going down, left side going up. And if I want to find the y-intercept for the rest of my life, when I want to find the y-intercept, I use x equals 0. So I plug in 0 in here, I get 3 times 5 times 1 times 2, and I get 30 as my y-intercept. So I could plot the number 30 anywhere I want. 30 seems good around here. I'm going to plot my x-intercepts. Negative 5, negative 1, and 2. And now I'm going to have to play connect the dots. I'm going to go from the left arrow to the right arrow, going through those dots. And I don't have to go exactly at that arrow. I just have to be going up on the left. So that one's not so bad. Through this x-intercept, through this x-intercept, through this y-intercept, and through this x-intercept, and going down on the right. You don't have to waver off to go get that arrow. And that's what it should look like. And if you look at it, I have 3 x-intercepts because it's an x cubed, and I have 1, 2 turns, a min and a max, a peak and a valley. Okay, another problem. Now we have a little bit more difficult factor here. It says 2x plus 5, but if I want to solve this for 0, because another word for x-intercept is 0, I would subtract 5, and I would divide by 2. So we can make that a little bit neater. Minus 5 over 2. This next one would be positive 1, and this last one would be positive 4. Those are my x-intercepts. My leading term, again, let's multiply it out. Well, there's no number up front, but the first parentheses is a 2x times another x times another x. I get 2x cubed. And because of this 2, the right side goes up to infinity, and the left side, well, this is an odd degree, the left side does opposite, goes down to negative infinity. So there are my little arrows going up and down. If I want to find a y-intercept for the rest of my life, I plug in 0. First parentheses, I get 5 times negative 1 times negative 4. I get 20 as my y-intercept, so I could plot my y-intercept as 20 up here. My x-intercepts are negative 5 over 2, positive 1, put it over there, and then positive 4. And again, I'm going to follow my arrows. I'm going to go from the left arrow to the right arrow, playing connected dots. I don't have to start way over here. I just have to be going down on the left, and I go from the down, x-intercept, y-intercept, x-intercept, last x-intercept, and up on the right. And there we go. Again, this graph has 2 turns, a maximum and a minimum. X to the third should have 2 turns in it. Okay, now we're going to look at when we have exponents on the outside of those parentheses when it's in factored form. Now, on the problems that we did above, like here, these when there wasn't an exponent there was a 1. There's a 1 there. Okay. Okay. That just means x to the first. That's why every single time we went through the x-intercept, it went through the x-intercept very cleanly through like a linear function goes through an x-intercept very cleanly. No bends or anything. No major bends. Except now we're going to look at things that maybe cause things to bounce or snake through a graph. Well, to me, something that bounces, that's because I have an x squared, or it has a parentheses squared, and something that snakes through has a parentheses cubed. Because an x squared graph is a parabola, it kind of bounces off an x-axis. And an x cubed function is a snake it's a little squiggle like this, and it goes through the x-axis, but it doesn't go through cleanly like a linear function. It kind of bends through what I call snaking through. So we're going to try these examples. I see I have 1, 2, 3 x-intercepts. -5 is the first, 1 is the second, 4 is the last, but some of them are special. I notice this first one has a squared, so this is going to be a bouncer. And this last one has a cube, so that's going to be a snake. Now I do have to find my leading term. I'm just going to put LT for leading term. And the first one is x squared because of this squared. The second one is just x to the first because there's no number on the outside of the parentheses. And the last one is x to the third. And I multiply it out and I get x to the 6th, specifically 1x to the 6th. So that means 1 means the right side will go up to infinity, and because it's a 6 even, the left side will go also up to infinity. When I want to find a y-intercept, I plug in 0, so I get 5 squared times -1 times -4 to the third, and if I do my math, I get 25 times -1 times -64. I get 1600 is my y-intercept. So I'm going to start graphing all this information. Right side goes up, left side goes also up, according to what we said. X-intercepts are at -5, 1, and then 4. But we did say there were some special things going on here. This at -5 is going to be a bounce. It's not going to go through the x-axis, it's going to bounce. And the one at 4 is going to go through like a snake. And then finally, our y-intercept is 1600. You can put 1600 anywhere you want on the y-axis. Now I'm going to go from the left arrow to the right arrow, following my pattern. Arrow, -5, oh, don't go through, bounce. Go through 1600, go through 1, and then I'm going to snake through 4. And that is what the graph looks like, hitting all those criteria. Now the next one, I'm going to do the same idea. I have 1, 2, 3 x-intercepts. Let's see, this is, again, be careful, -5 over 2. This is +1, and the last one, I know it's in reverse, but it's still x equals 4. We do have some special things going on here. The first one with the cubed is a snake. The second one with the squared is a bounce. And the last one has, to the first, it's nothing special. My leading term is going to be, well, the first one is going to be 2x to the third. The second one is going to be x squared. And the last one is going to be -x. There's my thing here. The last one will be -x. And I multiply it out, I get -8x to the 6. That means my right side with the -8 is going to go down, and my left side with the even power is also going to go down. I'll put little arrows here, down and down. And then my y-intercept, let me plug in 0, I'm going to get 5 cubed, -1 squared, 4. So that's 125 times 1 times 4. I get 500 as my x-intercept. I mean my y-intercept, excuse me. Now I'm going to plot everything. I could put 500 anywhere I want on the y-axis. I'm going to have -5 over 2. I'm going to have 1. I'm going to have 4. I have a couple special ones. -5 over 2 was a snake, and 1 was a bounce. And I could go ahead and draw my graph. I'm going to start here at this left arrow. I'm going to come up here. I'm going to snake through. I'm going to come up to 500. I'm going to come to 1. I'm going to bounce off 1. And I'm going to come through, and I'm going to go right through 4. Okay, and this is what the graph looks like of that polynomial function. So we have spent a couple pages of looking at equations and drawing some graphs. Now we're going to look at some graphs and make equations. We always have to do math in both ways. So the big things that we need to know, the big part of our equations were those x-intercepts. Those were the things inside the parentheses. So when we look at this graph, I have 3 x-intercepts. I have -5, -1, and 4. So my x-intercepts of -5, 1, and 4. And these x-intercepts create factors. Factors are the things inside the parentheses where x plus or minus whatever going on. And anything inside the parentheses with the letter x is its opposite. So it's going to be y equals, just like quadratics, always after the equal sign is the letter a, x plus 5, x minus 1, excuse me, x, this is a -1, my bad, plus 1, x minus 4. Okay, so this is where I start. I need another point. So to me, I try my best to use the y-intercept because it's easy to use 0 as my x. So my y-intercept is 0, 10. I plug it in. A. This is 5. This is 1. This is -4. I get 10 equals -20a. I get a equals -1/2. And this is where I'm going to check. A is negative. That tells me that the right side is going down, so a should equal a negative. That's how I double check my result to make sure I did everything right, by making sure the a value matches the right side of the graph. And I write my equation. I'll just call it f of x, -1/2, and copy up my roots that I had up earlier. And that is the equation of that graph on the left. Now, I'm going to do the same thing, but maybe a little bit more difficult graph, and I don't know why that pink thing is there. It came from the previous page. We're just going to deal with it. Again, I have to make note of my x-intercepts. I have an x-intercept here of -4, one here of 1, one here of 5, but some of them are special. This is a bounce, and at 5 it is a snake. So my x-intercepts of equal to -4, 1, and 5, but I do have to make note that this is a bounce at -4, this is a snake at 5. So when I write my equation, y equals a, always a. First set of parentheses, x plus 4, I got to put a squared on it because of the bounce. X minus 1, nothing special is happening there. And then x minus 5 with a cube because of the squiggle snake. Again, I try to use a point. I have to use another point, and I find a nice clean point, and I was lucky here. But pay attention to the scaling on the side. This is 0.40, not 0.4. 40 equals a 4 squared, -1, -5 cubed. 40 equals a times 16 times -1 times -125. And I get 40 equals 2000a divided by 2000. I get a is equal to 1 over 50, or you want to do 0.02. I don't care. It's the same number to me. And move up a little bit, and I get my polynomial function. I call it p of x is 1 over 50 x plus 4 squared, x minus 1, x minus 5 cubed. Oh yeah, I forgot to double check. My a value was positive. This right side is going up, so a should be a positive number, and it was a positive number. Okay.